Hi, my name is Bob Hassmiller, a district hydrologist for the Blue Mountain Ranger District. This photo is of a beaver dam that was present in the headwaters of Camp Creek in 2004. Now, it's an eroding stream channel with young lodgepole pine encroaching the valley bottom next to the creek. The objectives for this discussion are the existing hydrologic condition, emphasizing the storage capacity, valley characteristics, and water quality, then also quickly discussing climate change and some of the issues with snowpack vulnerability affecting low summer flows. Hydrology is a science that deals with water on the Earth's surface and in the atmosphere. Here we show a diagram of the many processes in the water cycle. Science is informing us that the existing upland forests may have tree densities that can be up to 3 times denser than what they were historically, resulting in increased losses of water that falls within the project area. Water losses are occurring in winter from the amount of snow that falls on the conifer canopy and is released back to the atmosphere through evaporation or sublimation processes. In spring, summer, water is pulled from the soil during photosynthesis, and these water losses are called transpiration. Water is the growth limiting factor in warm-dry plant association groups. Energy is limited in the cool-moist plant association groups. The departure from the historical condition in overly dense forested stands is affecting the water reallocation to the various understory layers of shrubs and grasses. All these things affect organic matter returns to the soil, an incredibly important part of the water sponge that is influenced through soils. We think of the water cycle as a mathematical equation to break it down and further understand the various processes. Outputs equal inputs minus that change in storage. The outputs are the amount of water leaving the system. The biggest pulse of water leaves the mouth of Camp Creek just before summer starts with a flood of water. This pulse does mechanical work and creates and maintains fish habitat. Water also leaves the system through evapotranspiration. Inputs, these are a fixed amount. Storage is key for this process. Storage has been affected by past activities, as we will see. Science has proven that watersheds with depressional wetlands are key to attenuating or dampening those peak flows. Soils store water in various clays or ash layers and can be increased by the organic matter mixing in high soil storing clays. Our valley bottoms and upland wet meadows were historically the biggest reservoirs for storing water, like a sponge, and slowly releasing it throughout the dry periods of summer. But our conditions, since trapping almost all beavers, construction of railroad grades down the middle of our valley bottoms, and channel incision, have severely altered this sponge effect from our landscapes. But we can do something about that storage component. We can control this piece with proposed management activities to improve resiliency. Hopefully you will understand more in this presentation about this key function in the Camp Lick project area. Here's a hydrograph, or a graph of the amount of water in the stream at its outlet or a stream gauging station over time. This graph here represents the water in Camp Lick project area through data obtained from DEQ. A water year starts in October when stream flow is generally low, extends through the rising limb to a peak flow, and recedes to the low summer flows, or what we call base flows. We will explore how alterations can affect the timing and the magnitude of peak flows and the amount and variability in the base flows. Precipitation zones range from 16 to 28 inches in the headwaters. The atmospheric river that hit in December of 2014 flooded Cougar Creek down. That is likely the transient range for rain-on snow controls over the lower one-third of the elevations within the project area. That's the yellow-green intersection on this map. Aspect also drives snow melt processes. South aspects lose their snow at least 2 weeks to a month earlier than those on the north aspects. These atmospheric rivers are just an amazing hydrologic phenomenon. They can carry up to 15 times the amount of water as the Mississippi River and originate out near Hawaii or the Samoan Islands. They affect our hydrographs on the Middle Fork about 16% of the time, yet 84% are dictated by the snowmelt flood runoffs. Hydrologic soil groups are based on estimates of runoff potential. Soils are assigned to one of 4 groups according to the rate of water infiltration. This runoff timing influences how much water and the timing of stream flows. The soils in the United States are assigned to 4 groups, A, B, C, and D, and defined as follows. Group A, soils having a high infiltration rate with low runoff potential. We don't have any of these in the project area. Group B, soils having a moderate infiltration rate. These consist chiefly of deep, moderately well-drained soils that have half fine texture and half coarse textured soils. These soils have a moderate rate of water transmission. Here in the Camp Lick project area, we have valley bottoms and some select other areas in green as part of that B group. Group C are the blue areas that are heavily observed in this map. Soils having a slow infiltration rate when thoroughly wet. These consist chiefly of soils having a layer that impedes the downward movement of water, or soils of moderately fine textured soil. These soils have a slow rate of water transmission. Group D are those observed in red. Soils having a very slow infiltration rate, high runoff potential when thoroughly wet. These consist chiefly of clays that have a high shrink swell potential, soils that have a high water table, soils that have a clay pan or clay layer at or near the surface, and soils that are shallow over nearly impervious material. These soils have a very slow rate of water transmission. This is the stream network and the 3 subwatersheds found in the Camp Lick project area. Please remember the shape of the watershed. 4 Corners, a popular place in Grant County. It's in the south central part of the map. And this watershed drains north to the Middle Fork John Day River. Yellow represents the small portions of private ownership within the project area. Water storage is critical. Meadows happen to be a big storage reservoir, similar to dams on the Columbia River. But why? The deep soil depth to bedrock, ash layers in the soil, and the high organic matter returns to the soil. The organic matter is that catalyst that brings the sponge effect. Low gradient and unconfined valley bottoms are very similar. They are depositional environments for sediment and water, plus all that riparian biomass that returns to the soil, creating high organic matter levels. The storage potential of valley bottoms is important during 2 periods. One period during peak flows through having the floodplain being inundated, and the other during low flows when floodplains have a water table that is controlled by the bed of the stream channel. We'll explore more with diagrams in a minute. Hill slopes store more water when soils are deeper, also in areas with Mount Mazama ashes and the various clays. The ash holds a lot of water, but releases it quickly. The clays can hold even more water. Clays are simply very small soil particles, and the better clays have a tremendous amount of surface area that can hold more water molecules and slowly release them. Organic matter plays that strong role of the sponge effect of water on hill slopes too. We will also focus this talk on the first two bullets. However, hill slopes and roads are always something we're investigating. But first, we're going to talk about the meadows, and particularly water storage. Geology is a big driver on soil development. Geologic pinch points can cause soil to build in places and form valleys or meadows. This map illustrates soil depth ranges across the project area from recent soil surveys. Dark blue areas have soils greater than 80 inches deep. That's over 6 feet deep of soils. These areas with deep soils have large water storage tanks on the Earth's surface. This allows us to focus our management activities on these critical areas to store and slow release water and improve the productivity within these project areas. Over 90% of these areas happen to occur along Camp Creek, in the stream bottom, and in the headwater meadow areas. The other location to recognize is the variegated landforms in the northwest part of the project area. These areas were landslides formed long ago under a different climatic regime. These forests have deeper soils with potential for more soil moisture storage and higher supporting biomass. Red areas have very shallow soils and have flashy runoff events, likely scablands. 3 major meadows occur in the headwaters of Camp Creek, and they include Coxie Meadow and Bear Wallow Spring Meadow and Whiskey Meadows that feed into Camp Creek. Let's take a closer look at each meadow and its condition. Coxie Meadow is the patch of green that you see in the middle of this photo. As you can observe in the inset map found in the lower left of this page, it is located in the headwaters of Camp Creek and in the southern boundary of the project area. This meadow was once much more larger in size and stored more water. The issues of channel incision or the down-cut channels affect all of these bulleted issues outlined to the upper right. The water storage and slow release functions have been lost. The diversity of native wetland plants has shrunken to the extent of the water table. This meadow is currently being utilized to grow great lodgepole pine. We are also currently attracting and concentrating livestock on this meadow because of a stock pond on the edge of the meadow. Let's take a look to better understand the issues affecting Coxie Meadow. This picture is a LiDAR hillshade, or a map that shows the surface of the earth. You see how flat the surface of this meadow is, except for those lines through the flats. These lines are what we call gullies or stream channels. These meadows should not have the energy to scour a gully. It should flow across the surface of the earth, or what we call sheet flow. Gullies are like irrigation ditches. They are effective at routing water off of these meadow features. Gullies are formed because there was once a lack of vegetation providing stability. These U-shaped lines, black, they are cross-sections that show the depth of the gullying at different locations, with graphs in the bottom left. These photos were taken along the line between those arrows. Since the channel has incised, lodgepole pine can establish and drink or transpire that water from the meadow. This section of the meadow is being transformed to a forest right before our eyes. This photo is taken at the end of the arrow looking upstream. Increased riparian biomass in the gully that is occurring in the northwest portion of the meadow due to the water table. Also, you can see lodgepole encroachment. Here is the meadow at Bear Wallow Spring. You can see the shades of green in this picture. The small ribbons of darker green occur where the water table supports wetland plants. This is a reduced extent from its historical condition. Again, the LiDAR hillshade illustrating the surface of the earth, showing the gullies draining the meadow. The cross sections show the gullies, once again where sheet flow hydrologic processes should be occurring. This photo is taken at the bottom of the arrow. It illustrates those ribbons of wetland vegetation in the gullies. The other areas show the dried out meadow portions with upland grasses, forbs, and weeds. Riparian biomass and biodiversity follow the water table. Rills, or miniature gullies, are at the base of this arrow. These rills are beginning to drain the major spring head at this site. Just to the north of the spring head is a trough, concentrating livestock on this meadow. Another gully that was likely a historic livestock trail that concentrated water and had little vegetative roughness became incised. This is the head cut, or the area that is moving the channel incision further into the meadow. This is the active agent in channel incision in lowering of the water table. Whiskey Meadow, also another headwater wet meadow, is plagued with the similar issues. This meadow is found in the northern portion of the project area and has 3 major spring sources to the left side of this map, and this meadow drains to the right or to the east. This meadow is perched by a basalt rim. The LiDAR hillshade in cross sections, again illustrating the channel incision in the meadow. This photo is showing the spring head with moderate to heavy utilization and a shrunken wetland extent. The other spring head that was historically fenced and had a spring box connected to a trough that's currently in a non-functioning condition. Decadent older willows dominate this spring, but lack younger age classes. More photos of channel incision, lowered water tables, dried out meadows, and encroached pine stands taking over the meadows. The bottom of this meadow showing more gullies and channel incision, loss of water storage, and an overall decrease in wet meadow habitats. Now, we're going to quit that meadow discussion and jump over to stream channels, their conditions, and how water retention is affected by the condition under 2 different processes of peak flows and water tables. Stream channels at a fixed location in a watershed are dynamic. Vegetation, beaver dams, large wood, and meandering channels provide roughness or resistance to flooding energy from that peak flood. A is in balance with watershed inputs, and we call this state in dynamic equilibrium. If sedges or willows are decreased, beaver trapped, and their dams decayed, and or large wood removed from creeks, they become incised, like that observed in figure B. Then they need to form a new floodplain through channel widening and then and only then, they will have the velocities in which sediment will begin aggrading and depositional processes will continue. Figures D, E, and F are all in that aggrading conditions. The incision processes can take place on scales of 10 to 50 years. The aggradation processes, or the valley formation, they take place under 500 to 1,000 year time processes to recover these systems. And these are the central tendencies documented through measuring cross-sections by USGS staff and researchers in the 1950s and 60s. The temporal processes, or time, must be recognized for recovery of these systems. Back to processes. Figure A exists where water flows above a flood stage and spills out onto its floodplain. Hydraulics drive gravels to deposit in the channel bed, and water is attenuated or dampened from floodplain storage. But when it's incised, the increasing flood depths stay in the channel, and this extra stream power transports the gravels through the system because of the higher velocities. Water does not spill onto the floodplain and therefore leaves the project area at an accelerated rate. This water is essentially lost to the Pacific Ocean and cannot be used by sedges and willows, nor slowly released during the dry summer months. Let's look to see how that process affects the hydrograph for Camp Lick project area. Again, here we have the reference condition measured from DEQ. But when we don't have floodplains being connected, we affect the hydrograph through an earlier peak, or the amount of water leaving the system earlier, and a higher peak of discharge, which can transport higher sediment, ultimately resulting in less base flows. Okay, now we're going to talk about the second process that occurs during the summer months when water is the limiting factor. Recall that we have condition B that has an incised channel. Please pay attention to the blue line that represents the water table. Because the stream bed is at a lower elevation, so is its water table. As a result of incision, the riparian vegetation have died because they no longer have roots that are in contact with this water. This allows the lodgepole pine to encroach, get established, and drink this water without limitations. So we've cordon aged these lodgepoles, and they're growing at unprecedented rates. Therefore, we are losing this water to the atmosphere and receiving limited services from that use of water. This is not natural at the proportion of reaches that it is occurring. Now remember A, when the stream is connected to its floodplain. So is its water table. It provides for wetland vegetation to have root systems that grow into and under the stream channel and functions like rebar to that soil and provides a tremendous amount of channel stability. We call this root reinforcement. The vegetation provides high quality shade and organic matter back to the stream and floodplain soils, the aquatic food web, and that sponge effect. Back to B. Now imagine that these deep floodplain soils have pore spaces between them that store water. This is the water storage zone that slowly migrates down gradient that we have lost. We are quantifying this in gallons of water based on the depth of soil and the width of the floodplain for our analysis. This water storage and supply is a service that functioning watersheds and nature provides. Let's work with this because we are facing a changing future climate, as we will soon see. This riparian vegetation is just critical to allow beaver to manage the water resources from these systems. We often talk about prioritizing areas that have more potential than others. Valley form characteristics often define how a channel can adjust to watershed and reach changes. Valley confinement is a measure of the form of the valley, and this is often imposed by geological constraints. The confinement of the valley is key to how water and sediment will be stored within the valley and how a stream energy can achieve a dynamic equilibrium. Here, we characterize valley form. Unconfined valleys have ratios greater than 4, as seen on the left side of this diagram. The valley width is 40 meters, and the active channel is 10 meters, with a ratio of 4 in unconfined. The picture of the unconfined valley is also shown below the diagram. Then we have confined valleys, where the ratio is below 2. In the middle are moderately confined valleys, with a ratio between 2 to 4. This allows us to stratify or map a project area out. Unconfined valleys have differences in hydraulics because they can adjust laterally or side to side across the valley to those water and sediment inputs. Because of this, smaller grain sizes get deposited, let's say the size of gravels. These gravels form riffles that shape pools and meandering channels. As water flows through the riffles, it mixes with the subsurface layer that drives hyporheic exchange. It forms pool riffle channel morphologies, or forms, and there tends to be more riparian vegetation of willows and sedges in open valleys. Hyporheic flows is again that water that flows through the stream bed and mixes with the subsurface water layer. This actually cools the water down, changes or processes nutrients, and these areas have robust aquatic bug diversity. The confinement of the valley is a dominant characteristic for driving pool riffle channel types, as seen in this pie chart from John Buffington's work. Unconfined channels tend to have a disproportionate share of pool riffles as compared to other channel types. These pool riffles are key habitat types for juvenile salmon. We measured the valley width of Camp Creek from the mouth of the river at River Mile 0 with the Middle Fork John Day up through to Coxie Creek and to the split of the East Fork Camp Creek near River Mile 15. This graph shows the valley width located on the y-axis as you travel longitudinally or up Camp Creek from its mouth. This is what the historical extent was and what the potential is. However, as we'll see, it's been slightly changed. We break streams into similar types of units called reaches, and we happen to have 9 of these in this length. Reach 1, starting at River Mile 0, has valley widths up to 600 feet across the valley. Reach 6, in orange, and it's the most narrow for Camp Creek. It flows through a gorge with bedrock cliffs on both sides of the channel through this. Then it widens as we move into the headwaters. Please recall, major valley width with deep soils can potentially store higher quantities of water if in a functioning condition. As we look for the average channel width, the average valley width, we get the confinement for that reach. Whoa! It's so important to note that these things in Camp Creek are very different than most other project areas for having these broad, wide, unconfined valleys. We're exceeding that ratio of 4 for all reaches except for 6. This Camp Creek should have major water storage and gravels galore, hyperetic cooling, and pool riffle habitats everywhere. But for some reason, something seems to be wrong. Camp Creek Reach 1 is located at the bottom of Camp Creek Watershed and flows into the Middle Fork John Day River. At the bottom of this diagram, you can see the bridge that crosses Camp Creek and is the upper extent of Reach 1. The orange mapped areas represent the toe of the valley from one side to the other, or the historical floodplain. The blue mapped areas are the width of the current channel migration zone due to channel incision. We surveyed the channel characteristics with a laser level to evaluate the channel and floodplain form at the location of the black line. The diagram to the right is that survey or cross-section. The peak flows get trapped in the incised channel because of lack of floodplain connectivity. Gravels and accelerated amounts of water get transported through this reach, as opposed to being inundated in a depositional reach. Most of the log weirs that were placed to capture gravels in this reach were undermined because of the high stream power. The floodplain to the right also requires to be irrigated to provide forage for livestock use. This is a result of the water table being lowered and the valley being dewatered. The loss of floodplain connectivity has altered the functions and services that nature provides when in a functioning condition. Here's a diagram on the left of the 1939 aerial photos of Reach 1 with the aerial photos from today. As you can see, this section of the floodplain has dried out since the 39 aerial photos due to channel incision. Camp Creek Reach 3 starts at the private ownership boundary. Again, the blue is the active channel migration zone, orange, the historic channel migration zone, and the black dashed lines are old railroad grade lines and spurs that currently block floodplain connectivity and inundation and is behaving like a levee. These levees have degraded floodplain connectivity processes and are the root causes that inhibit water storage, limited riparian biomass, and biodiversity across the floodplain. It increases stream power to transport larger materials and forces the channel into one long riffle, lacking pools where they should be present. This reach lacks high-quality shade from that riparian veg community. These photos illustrate the log weirs that tried to treat the symptoms, but not the root cause constriction. As a result, 90% of the length is riffle dominated from our stream surveys. 13 pools exist in this length, where 43 should be present, to provide high-quality rearing for juvenile steelheads. 9 of those 13 pools were behind log weirs. The other 4 were formed by stream bend meanders. Channel incision has altered floodplain connectivity processes where beaver dams and complex stream channels and willow communities should be abundant. Camp 4 is similar, but has other interesting observations. It has 2 unconfined valley bottom sections here. Then there's a great landslide and alluvial fan that also influences valley confinement and aquatic habitat. The unconfined reaches are affected by railroad grades again. Valley cross sections illustrate the disconnection and floodplain connectivity originating from the railroad grade levee still being present between the channel and its floodplain, as you can see in the hump around width of approximately 150 feet. These photos also illustrate a larger substrate stream bed and a dried out floodplain. Finally, the portion of the reach that is mostly confined. This is where we stopped this past summer and had lunch with the Blue Mountain Forest Partners Collaborative looking at the beaver dams. The railroad grade is still present, but does not affect the processes or functions in this section. It's therefore largely in a resilient condition. Reach 8 is higher in the watershed and also exhibited signs of channel incision. No railroad grades were present in this reach, but beaver dams were likely much more abundant historically. The bankful channels trapped in the gully by depths more than 2 feet, and as a result, lodgepole pine have encroached the channel and floodplain and are cumulatively working to dewater this section of the Camp Creek Valley. These factors reduce the extent of willows, cottonwood, alders, and other sedge plant communities. This graphic was obtained from the CHAMP monitoring program and is an excellent example of how erosion occurs in the headwaters and source areas and is transported through tributary channels and deposited in the accumulation zones where valley width and gradients allow sediment to fall out during peak flows. This is a map illustrating Montgomery and Buffington channel types based on stream gradients. The red lines represent the source areas where sediment, just a fancy word for soil, is captured, stored in large amounts, awaiting a debris flow or a landslide to become activated. Wildfires and post-thunderstorms drive the biggest pulses of sediment inputs within the project area. Orange and yellow lines are cascade and step pool systems with stream slopes ranging from 4 to 20%. Green, purple, and blues all can be pool riffle systems with slopes less than 4%. These are the response zones that deposit sediment and build floodplains or meadows. These are the creme de la creme for aquatic habitat because of this gravel deposition. Focusing in on Camp Creek again, this graph shows elevation on the y-axis with the mouth of Camp Creek at River Mile 0 and extending up the watershed. Each red line represents the various reaches. The changes in the line are due to geological constraints on the creek. Again, looking at the stream slopes, Camp Creek is almost entirely a depositional reach, particularly in these unconfined valleys, except where past human features are accelerating this channel incision process. Now, jumping over to water quality, the integration of this hydrology, riparian conditions, and their stream channels. The two issues that have manifested themselves through 303D listed activities are biocriteria, or the lack of a healthy aquatic bug population, and water temperatures, where it was historically 303D listed until a TMDL document came that gave guidance on management. Again, these two are issues because of the conditions of the watershed. Water temperatures were measured at 25 locations throughout Camp Creek, these green points, to understand cool water inputs and water temperature trends. This graph represents Camp Creek near Sulphur Creek. The device takes measurements every hour of water temperatures. On the x-axis is the date, and on the y-axis is the stream temperature in degrees Fahrenheit. It was placed in the stream just after July 15th and taken out in mid-September of 2014. There is variability in day and night water temperatures and throughout the summer. We call the day and night differences diurnal variability. This effect is exacerbated by the amount of shade riparian vegetation provides. As you can see, this effect is greater than 10 degrees Fahrenheit. Further, the amount of water and the hypereic flows that we talked about earlier, they both work to dampen this diurnal effect and provide more resiliency in temperature fluxes that strongly affect fish. In 1977, the Camp Creek wildlife/livestock exclosure fence was erected. Its purpose was to provide information on the effects of big game on riparian areas. It was to be coupled with upstream livestock exclosures and contiguous areas open to livestock grazing. These analyses have not been completed at this time. However, the photo points show changes which have taken place inside and immediately outside of the exclosure. The exclosure is within the Long Creek allotment. At the time the exclosure was established, the allotment was going into a rest rotation system. The outside of the exclosure was receiving 55% and greater use by livestock at the time. In 1982, a fish habitat improvement project was initiated on Camp Creek, consisting of weir installation and fencing to further control livestock use. The fence was completed in 1983, and a 30% utilization standard was set on Camp Creek for use by livestock. The area directly in front of the exclosure has generally received this amount of use, as it is a key area to livestock when in this unit. The unit around the exclosure received a 1-year rest between 83 and 85. The allotment went back to a deferred rotation system in 85. It should be noted that at shrub transect locations, both upstream and downstream, from 49% to 60% use on shrubs by big game has been recorded when livestock had not been in the unit from 83 to 85. Current conditions are shown in the 1988 photo. It's very important to note that it appears that not only livestock, but big game can substantially affect the rate of recovery of the shrub component in these riparian areas. This photo is of East Fork Camp Creek at the headwaters of camp. It was very open and lacked shrub and downwood complexity and was largely used as a managed and wild ungulate corridor for movement. As a result, shrubs were being browsed at heavily used rates. Wood was felled to create complexities to allow for shrub germination areas and to break up ungulate connectivity up these sensitive areas. This will aid in getting shrub diversity and age class structure restored, critical for beaver habitat into the future. Headwater tributaries of Camp Creek were also logged historically and lacked coarse wood jams. As a result, incision has occurred, exposing tree roots from accelerated runoff rates. These tributaries could also function to slow down the movement of these peak flows and store water. Roads are plentiful in the Camp Lake project area. Road densities are high, averaging 5.6 miles per square mile. This affects fine sediment leaving roads and entering streams. Roads cutting through hill slopes with deeper soils and routes that intercepts that water and routes that water through the road ditch network to the stream and out of the watershed at a faster rate. There is approximately 60.3 miles of road within 100 feet of streams in the project area. These roads constrain channel migration zones and reduce the amount of wood supply that could be recruited to the stream network. Roads at this density levels do not get maintained regularly. So culverts are commonly blocked in the project area. As a result, water continues down the ditch and begins to concentrate, eroding the clayey Clarno soils that have limited infiltration rates. This water also gets directed off the road to a hill slope before entering a stream. Excessive energy isn't being dissipated, and so therefore this water cuts into the soil. Roads were surveyed this past field season for condition, and numerous gullies were found in the project area. These points represent gully erosion from the road network and the potentially connected to the stream network. When culverts block, peak flows flow across the road and add fine sediment inputs to the stream network. This sediment decreases the number of bugs that can live in the stream. Landslides also affect maintenance needs on segments of roads within the project area. Clayey soils, driven during wet periods, also cause significant rutting, and sediment can be transported that degrades road conditions. Green dot road closures provide seasonal driving restrictions and quality hunting experiences in select roads in the project area. These seasonal closures improve water quality, wildlife habitat, and public satisfaction. Recapping on the conclusion on the condition of water, our storage reservoirs are currently in a poor condition. Our meadows and valley bottoms have incised and are moving water off the landscape at an accelerated rate. They have much more potential. This is because roughness elements have been removed or altered. It's time to look at the root causes of the issues and improve resiliency for the processes and functions that nature provides to current and future generations. So what does this mean? Less and warmer water, less biomass and biodiversity for forage and habitat. It lacks resilience, and ultimately, it reflects these issues of channel incision. Abundant, cool water is what functioning watersheds supply. They provide this for drinking water and irrigation for our crop needs, for fish and animals. Water is also precious for riparian vegetation needs, providing cottonwood galleries, willow communities, and sedge floodplains that provide shade and wildlife habitat. Shrubs drop leaves that get caught on the floodplain and break down into the soil horizons and add organic matter. Remember, organic matter returns to deep soils provide for the sponge effects of water retention and storage. Nutrient cycling also dominates aquatic food webs and helps to grow fish quick, and has many different aquatic bugs through biodiversity. In the uplands, water retention helps grow trees, forage, and shrubs that help sustain society and wildlife. I like to think that returning these watersheds to functioning conditions through restoring the root causes that truly impede resilience will reduce government restrictions. Finally, the future isn't so bright for the Blue Mountains. We are anticipating an increase in air temperature of 3.5 degrees Celsius by the year 2080. Recall that snowmelt hydrograph we discussed earlier? Well, it's expected to go away. This will result in no more snow for the Camp Lick project area for future societies. This means we will see more rain events happening in the winter with that water not being tied up in snow, but released to the Pacific Ocean much quicker. As a consequence, we will see less low summer flows in August and likely warmer water temperatures. We really need to think about the beaver populations that once existed before humans trapped them, according to our historic journals, and ultimately the benefits that beavers, these unconfined valleys and meadows provide to humans and wildlife. Thank you for listening and considering the crisis we face with water supply for future generations.